Hi there, exercise 11A for your integration, and now it's actually quite a lot of different types of integration we're going to say. It does say a range of new functions. So I want to get on and crack on with this. Now a starter initially is actually differentiation. It's a reminder of stuff you've seen in chapter 10, I think it was. So if you differentiate this, the rule basically says we can use the chain rule, and that means I think of this as just a thing x. So I'm going to write 5 lots of 2x minus 1 to the 4, but then I have to differentiate this bracket, which is 2, and that gives me a final answer of 10 lots of 2x minus 1 to the 4. This is something you're meant to be able to do. So again, treat this as an x thing. So 3 comes to the front, times by 3 gives me 9 lots of 1 minus 2x squared, lose a power, and then times by, and now it's minus 2 because of minus 2 there. So that gives me minus 18 lots of 1 minus 2x squared. This next one, well, obviously first thing to do is to note that this is really x plus 2 to the half. And you'll notice all of these are the same. I times by the front, half lots of x plus 2. Now lose a power, so it's the minus a half. And here I've got a times by, well, it's actually times by 1. So my answer is a half lots of x plus 2 to the minus a half. And the last one here, again, probably best to write it as a proper power to the minus 1. Hopefully you knew that. So times in by the 2, I get minus 2 lots of 5x plus 3, lose a power. So that's minus 2 times by the differential of this, which is 5. So my final answer here, I'm going to write minus 10. And this thing, I'm going to put on the bottom as 5x plus 3 squared. So if we just check the answers, let's see what I've got. Yep. Oh, that's interesting. That one I didn't put back as a proper power, like a square root thing, which is better written like the way I've done there. And that one I did remember to. So all of those are right, and now we're going on to integrations. And you'll notice at the top, it just misses it off. We're integrating these type of expressions, ax plus b to the n. Notice this is not an x squared thing. This is, with integration of these things, it only works if the function is said to be linear. So the inner function, so here 3 plus 2x, yes, that's just so many x. 1 plus 2x, yes. If it said 3 plus 2x squared to the 5, can't do this. This rule will only work if this is a linear thing, so no to this. And the rule is the opposite of what we saw before. Before we were timesing and then knocking off a power and then timesing by the inner power. So everything we do is based on that. It says integrate the outer function, divide now by the derivative and add a constant. So let's do an example. Oh, this is the posh formula. You can write this down, but what you'll notice is, so if you've got kax b to the n, we add a power, so it becomes n plus 1, and we divide by that power. So we add a power, divide by that power, plus c. So that's it. So, plus, of course, you'll notice the a has gone onto the bottom as well, and that's what it says here, the divide. So that's it. So if I do this one, 3 plus 2x, let's just checking where the answer goes, 3 plus 2x to the 4. So what I want to do is 3 plus 2x, add a power, divide by that power, but don't forget to divide by this too. So this is a tenth of 3 plus 2x to the 5 plus a constant. And there it is. Second one, it says 1 plus 2x. The first thing I want to do is write that as 1 plus 2x to the half. So when I integrate that, I'm going to get 1 plus 2x. Now I've got to add a power. So that's 3 over 2. Then divide by that power. 3 over 2. And also divide by the 2 there, the differential of 1 plus 2x. And you'll notice they cancel. I end up with a third of 1 plus 2x to the 3 over 2 plus a constant. And my last one, now it says, again, I need to write this as 2 lots of 1 minus 3x to the minus 2. So when I integrate this, it's two lots of 1 minus 3x. Add a power, that's minus 1, be careful. Divide by that minus 1. And also divide by this minus 3, so it becomes a times on the bottom. Obviously minus and minus is a plus, so that's two lots of 1 minus 3x on the bottom because it's a negative power. And there's actually to the power 1, and that's 3. So you could put the 3 like that, or you could make that 3 minus 9x. I just left it like that. All of them need a plus c. So that's quite nice. Now integrating e to the x is relatively straightforward. Again, the kind of expression you get, well, in its simplest form, we've seen already if you differentiate e to the x, you get e to the x. So it's no surprise to learn if you integrate e to the x, you get e to the x. But you get other versions of it as well. So if you've got a to the ax plus b, notice the a here ends up on the bottom. It's a division again. With differentiation it's times, so here it's division. And so if I do these examples, now notice this one then, I'm going to get 2 when I integrate e to the 5x. But because it's a 5, I have to divide by that 5. Notice the 5x stays as a 5x, doesn't change, plus a constant. Okay, and this one here, it's e to the 1 minus 2x, so it's e to the 1 minus 2x. But notice, although the power stays the same, well, I have to divide in this case by, well, 2 minus 2. So I'm going to write minus a half e to the 1 minus 2x plus a constant. There it is. And here, well, I've got, it's e to the 2/3 of x, so I can write that down straight away, plus a constant. The only thing is, what happens when I divide by the power? 2/3 becomes 3 over 2. 3 over 2, e to the 2/3 of x plus a constant. There we go. Nice and straightforward. Now you also have to integrate 1 over x type functions. So functions of this type we also need to be able to integrate. And it's a bit weird because there must be an answer when I integrate, but there's a problem because my power says add a power and divide by that number. Now notice if I have a function and for instance I'm asked to integrate 1 over x dx, then and I'll better do this between two values, so that's between 1 and 2. That's the suggestion here. Now, this probably is better written as a, with a proper power. So I'll write e to the x to the minus 1 between 1 and 2. And my rule says add a power and divide by the power. So if I add a power, I get minus 1 add 1 is x to the 0. And this is the problem. I therefore am meant to divide by 0, and you should by now know that dividing by 0 is a bit dodgy. You can't do it. So therefore it kind of implies there is an answer, and yet this is what I'm saying, there is an answer. There's definitely an answer because there's definitely an area under this curve. This is the curve of y equals 1 over x. There definitely is an area under it. There definitely is. It's just that I haven't got a formula as yet to find this area out. So there is an answer, and this is the formula we're going to have to use. And weirdly, you end up, if you integrate 1 over x, you get log x. And log and mod x as well. If it's a negative, you ignore the negative. So bear that in mind. There's this harder version here. If I integrate, you can't quite see it here. It should say ax plus b. So if I've got k over ax plus b, and ax plus b is on the bottom, then my answer is k over a log of ax plus b plus a constant. So bear those two formulas in mind. You can just about make them out here. That's a k on that one, a k on this one. So I've got to integrate this. So first of all, just notice it's very similar to this. So my answer is going to become 2 divide by that 4, because when I integrate 1 over 4x plus 1, I get log of 4x plus 1. And you'll notice the only thing I've had to do there, or plus a constant, the only thing I've had to do there is, it says 4, so 4 went on the bottom, and it became a log. Obviously that becomes a half of log of 4x plus 1 plus constant. Now this is a bit more complicated, but only because it's got these two separate things, and you think of them separately. So if I integrate 2, I get 2x, add a power. That was just a straightforward one from year 12. But if I integrate this, I get log of the bottom, 1 minus 3x. Notice, please, you then have to differentiate it, which gives me minus 3. So actually it becomes minus a third, and I divide by that minus 3 plus a constant. 2x minus a third. Yep. So everything there is fine. This last one says integration of trig functions. We have already seen that when we differentiate sine and cos, we have this rule. And you can move down through the sines and the coses, and I just write sine, cos, minus cos whenever I get this. And I know if I differentiate, I go down, but if I integrate, I go up. So that's the integration of sines and cos and differentiations as well, obviously. But there's more to this than we've seen so far, because from chapter 10 differentiation, we basically were given some differentiation which are similar to this. Now this is what the formula sheet says. The formula sheet says if I differentiate tan, I get sec squared. You notice kx gives me k sec squared kx, and it gave us these others. This is what the formula sheet gives us. Now this then we can take from it. So you'll notice here it says tan differentiate gets sec squared. From this we can say to ourselves, if I integrate sec squared, I get tan. And that's what I wrote there. Integrate sec squared, I get tan. And all of these are useful. They tell us that sec differentiates gives sec x tan x. But likewise, I can work backwards. I can use that information. I can do that for all four of these. So if I get given something with cosec x, cot x, I know it's going to have some cosec x in my answer to my integration. So bearing that in mind, we're going to try to do these again, but this again comes back to the chain rule. This is really what this is saying. So if I integrate trig functions, I'm going to have to use this. So for instance, integrate cos 3x. Integral of sine, cos and stuff, we just said, if I integrate cos, I get sine. So I know my answer is going to be sine 3x, but because it's got a 3, divide by that. So it gives me a third plus a constant. Sine of 3x over 3 plus c. Sine of 4x. Now again, I'll write it here. So sine becomes, from this rule, minus cos of 4x. But because it's got the 4, I'm actually going to write minus a quarter of cos of 4x. And the last one says cosec cot. Oh, now that looks like a formula we had before. Cosec cot. Notice, if it's cosec, it gives me minus it. So the minus goes with it. I reckon it's minus cosec. So I reckon this is going to be minus cosec of 2x plus 1. But notice it's 2x plus 1, so I've got to differentiate that. It gives me 2, so therefore it's minus a half of that plus a constant. Minus a half of that plus a constant underneath, it does say that. So we've gone through quite a lot there. I mean, the 4 methods we've gone through, of course, remember these as much as you can. Let's just talk about each one as I've got a few seconds. So if you are integrating ax plus b to the n, you treat it like you would normally, you integrate the outer function as you would normally add the power, divide by the power, but then you also have to divide by the derivative, and we saw that. Lots of examples there. We integrate e to the x, and if you have e to the ax, it becomes a bit more complicated, but basically the a drops down to the bottom. So we saw this here, where it was e to the 5x, and it becomes 2/5 of e to the 5x. The 5 jumped down to the bottom. We saw the 1 over x type functions, and we now know that it becomes log of x. So if I integrate 1 over x, I get log of x. And the only thing to worry about there is if it says, say, not 1 over x, but say, in this case, 2 over 4x plus 1, the 4 goes on the bottom as well as becoming a log. And the last one was these trig. Now, we're going to use the differentiations to tell us the integrations. And we saw only a couple of examples, but we saw those, and hopefully they made sense. So that's enough for the lesson, and in the lesson we'll go through some examples.